Good morning or afternoon, depending on your location. We are here today for our AC coupling webinar. I am here today with Ryan Stankiewicz, who is our applications engineer. I am Sue, your North American sales manager. All right, and throughout this webinar, if you do have any questions, please go ahead and put them in the questions pane, and we will try to answer all of those as we go along. And of course, we will have a question and answer period at the end. With that, I'll go ahead and let Ryan get started on this for you.
All right, thank you, Sue, and appreciate everybody taking their time to come listen to me ramble about our AC coupling with our Rosie inverter. So briefly, I'm going to give you a little backstory. Some of you probably already know who I am. Those that you don't, I'm an applications engineer here at Midnite Solar. I've been in the solar industry for pushing 20-something years. I did off-grid installs for quite a period of time before that, and I'm also a licensed master electrician. So there's a little bit of experience to fall back on. My door is always open to you guys. Most of you probably already have my cell phone number. Feel free to call anytime, any questions, more than happy to help. So we'll jump right in. And for those of you that don't know who I am or who Midnite Solar is, this is just some of the stuff. That's Robin Gudgel pictured on the right. He is the founder of many of these companies, but he was an instrumental part in Trace Engineering, which got bought out by Xantrex. He then helped a lot with Magnum Energy, getting that off the ground, and at the same time founded Outback Power. And then he came over here and founded Midnite, and this is just some of his old legacy products. We don't have much Midnite product in there, but that's some of the stuff he's been involved in up to that. So to say we've been in this for a while is kind of an understatement. It's kind of fun when you come out and see our facility, see our people. If you've been in the industry for a while, you'll see faces you recognize. You might see, Darren Emmons, who's from Outback, or Tony Boatwright, who comes all the way back from Trace Engineering. So just a really great bunch of people, a lot of exceptional talent, some really great products. We like to say that we're one of the most innovative manufacturers in the industry. We try to fill a need whenever we see a need. We try to react to your feedback. I've literally watched Robin set at a show in the middle of a cow pasture and work with the installer and move knockouts on an E-panel to make it more convenient to install in the field. That's kind of how we work. I actually just got off the phone with one of our engineers to change a bus bar to make it more versatile. So little things like that. We really do react to your feedback. We listen to you guys, and we work on that. One of the largest manufacturers of PV combiner boxes in North America, and of course our world famous classic charge controller. We are now closing in on 100,000 of those things out the door. That's pretty amazing. We've been doing those for a little over 15 years now. A lot of new technology going into play, a lot of exciting things coming down the road that I'm not going to talk about right now, but just a lot of exciting stuff happening at Midnite. So why you're all here is to learn about AC coupling, and I will talk a little bit about our all-in-one as well, but it'll be pretty subdued on the all-in-one. That will be a webinar all in itself, really, because there's a lot to AC coupling. So with that said, we're going to go over the Rosie specs real quick for those of you that don't know the Rosie or aren't completely familiar with it. But it is, a 7,000 watt inverter, and we'll talk about that. We're going to explain what AC coupling is. We're going to talk about some of the pros and cons. We're going to help you understand how you would size the system, some wiring scenarios, some of the basics of programming, theory of operation, and as well, I'm going to explain to you how to do a functional test. That last one is probably one of the most common things I see missed. I'm guilty of it myself as an installer, where everything's working, you're tired, and it's like, yeah, I'm ready to go home, everything's doing what it's supposed to do. With AC coupling, there's definitely another step that we need to verify that functionality, because there's a lot of risk if the functionality isn't correct, and we'll explain why as we go on. So the Rosie is something that we're extremely proud of, super excited. It's a game changer. The thing is a powerhouse. It's very versatile. So a single Rosie can do 120 volts, 60 hertz, 120 240, 60 hertz, 230 50 hertz, or 120 208 two legs of three phase, 60 hertz. But if you need three-phase, full three-phase 208, we can do 3 Rosies. So it's very, very versatile product. It's very lightweight. The thing weighs about 43 pounds. It is screened so that bugs and insects and stuff don't get into it. It is not outdoor rated. The Rosie, like all of the rest of the Midnite Solar products, except for the all-in-one and the PowerFlow 16, are indoor rated. It is listed UL 1741. The mobile version is UL 458, and they are both listed for Canada as well, CSA listed. The Rosies have a couple auxiliary input-outputs that you can use to drive things like automatic generator start, a diversion load, a vent fan, et cetera, et cetera. Just a lot of functionality there. 120 amp charger. So at full boogie, the Rosie will charge at about 120 amps DC. Some generators, if the generator is not real clean, will be a little less than that, but it'll be close to that. And you can stack Rosies in parallel. We talked about 3-phase, but we do support, currently we support up to 2 Rosies in a 120/240 stack for 14 kW. We do have many test systems out there that are larger than that, and things are looking real well for going more than 2 without any problem. Surge capability, I've told you a couple times, the thing is a powerhouse. It will surge basically 3 times its rating. I've watched this thing start 20, 21 kilowatt, low surge loads, and it doesn't blink an eye. So it is very, very robust. It does do state of charge monitoring with the Whizbang Junior if you're using an open loop charging scenario with like lead acid or a lithium that's not supported. It also does closed loop with our PowerFlow batteries as well as any other battery that uses pylon. So when we did the PowerFlow battery, when we partnered with that ODM, we went with the pylon protocol because that seems to be sort of taking over as the dominant protocol, if you will. There are other protocols out there, but that one seemed to be kind of winning the race, and that's what we went with. So if you have a battery like an EG4 wall mount or a regular EG4 with the EG4 communications hub or other batteries, you can set it to speak pylon. Some of them use different words for that. So if you run into an issue, like I believe on the EG4 battery, it's called Solarc mode, and that turns it into pylon. I think another battery I was working with the other day, they had Victron in there, and Victron is a pylon protocol. So if you get into some mischief, give us a call. We can probably help you through that. We talked about, the die-cast aluminum closure. So that is one neat thing. These things feel very nice. They're a quality feeling item. It's all die-cast aluminum. It has a matching breaker box you see there in the picture that fits below it. If you're doing a stacked, we have a primary and a follower E-panel that goes with that. We also have the optional back plates and matching charge controllers, which we won't talk about in this slide deck just because we're talking about AC coupling, but you can mix AC and DC coupling. Full featured automatic generator start, 2-wire generator start. So you've got your blackout times. You've got, several reasons that you can start on state of charge, voltage, time of day, etc. Then you can stop on multiple reasons, state of charge, voltage, time of day, or going to float. And you can set multiple triggers. So you could tell it, hey, I want you to start at 50% state of charge. And then you can also tell it, hey, I want you to start at 48 volts. So if for some reason the state of charge gets off, the voltage will still kick in. We talked about quiet time, and whatnot, and exercise time is also in there as well. We do include the battery temperature sensor with these. If you're using a lithium battery, you still can use the battery temperature sensor. So that's a change from like the classic. On the Midnite Rosie architecture, the battery temperature sensor can still be used. And when you select lithium, it'll disable temperature comp, but it allows you to set low temperature stop charge. So instead of the BMS having to control you charging the battery, you can set the equipment to stop charging at, like 30 degrees or 32 degrees or whatever temperature if you're not using a heated battery. And remote battery voltage sense. That's something you guys all begged us for on the Classic. Classic unfortunately didn't have enough processor pins left to add that. So we have added that on our new products. So all of our new products have remote battery voltage sense. So if you're using a open loop communications, you can wire up that remote battery voltage sense, and it will take care of any resistance in the battery wiring and accommodate for that. All of the new products do speak CAN bus. We do have a publicly available CAN bus document if you want to monitor your own CAN bus. We have also partnered with Solar Assistant, and you can pick up a Solar Assistant and plug in and do your monitoring as well. And the last feature I like to talk about, which is probably to me is the more important feature, is that it is still actually built in the USA. It is built right in Arlington, Washington. We build our own circuit boards, we assemble, we test, we do everything right there. All engineering is done in Washington. So it's a true, kind of last man standing American-made inverter, if you will. So that's something we're quite proud of. So we're going to jump in and what is AC coupled? It can be kind of a mysterious term. I remember when I first heard it, I didn't understand, and I sat down with a couple industry professionals and really got my head around what it was. It's basically a controlled backfeed of a battery-based inverter. So you'll know if you've installed many off-grid systems, you'll know we always preach never, ever, ever, ever backfeed that battery-based inverter. Never connect any power source to the AC out of that inverter. You will damage that inverter. That's been hammered into you for years and years and years. Well, now we're going to tell you go ahead and connect that source to it because it's a grid tie inverter. And the grid tie inverter will actually regulate and synchronize. So that's how we get around this. That's how it's okay. If you could watch it on an oscilloscope, and I've got a video out there I'll try to remember to put up on Facebook when we're done. If you could watch it on an oscilloscope, you would see that the Rosie will move its sine wave back and forth a little bit and up and down a little bit until it locks to the other inverter, and then or the grid tie inverter will do that. Actually, I'm sorry. The grid tie inverter will move its sine wave around to match the Rosie, and when the two match, they lock together. It's the same thing the Rosie does when it connects to the utility grid, or any battery-based inverter when it connects to the utility grid. So it'll synchronize, then it will lock, and then it will ramp slowly, and that's where we get the fact that it's okay to do. And again, the GT inverter, grid tie, in this case, GT stands for grid tie, will actually shift its phase angle and everything to lock. It's kind of fun to watch happen in real time, and it does work very, very well. So batteryless grid tie inverters, so your N-phase or your AP systems or your SMA, Sunny Boy, they all require that reference to the grid before they can actually do anything. So they require 120, 240. They do require the neutral. And when they see that, if it's within their spec, they will then connect to it, synchronize to it, and then start pushing power back. And that's what makes this, okay. They are responsible for the anti-islanding still, because if you have a Rosie and a Sunny Boy, let's say, for example, connected to the utility grid, when the grid fails, the Rosie will open its relay and everything's good. The battery-based inverter provides the signals we talked about. And it's also important to note that not all battery-based inverters can AC couple. So it's not just any battery-based inverter that can be driven backwards, which is what you're doing in an AC coupled situation. You're actually driving the inverter backwards in sort of an uncontrolled state, if you will. The control is the batteries absorbing that power. Not all batteries have not all battery-based inverters have a 1-to-1 ratio. And we'll talk about what that means later, but that's just something to be aware of. Just because we tell you the Rosie will do this and it has a 1-to-1 ratio and it frequency shifts, doesn't mean that X brand inverter that you may buy off in eBay will do the same thing. That may end poorly. It may blow up and go up in smoke and be done. It has to be an inverter that can run bidirectional, and not all inverters, especially lower cost inverters, will run bidirectional. A lot of them have a separate charger module rather than a bidirectional inverter. And as the last bullet point says, not all battery-based inverters frequency shift, and not all of them do it in a, a logical way, or it's not logical in how you, or intuitive, that's what I'm looking for. It's not always intuitive how you would do that. Like on a Magnum PAE, for example, you have to put it in custom battery mode in order for it to frequency shift. The Rosie, you have to enable AC coupling, and I think like the Snyder products, you also had to enable AC coupling to get frequency shift. But some inverters just won't frequency shift, and the ones that won't, you need to do some form of a blackout relay on the grid tie inverter that will kick it offline or remove its grid reference when the battery is full. What we used to do on products before we had the Rosie, we installed a 2-pole relay in there and we drove it from one of the auxiliaries that would, when the battery voltage exceeded a set point, we would open that relay and disconnect the grid tie inverter. So for the purpose of this pros and cons, some of these are generic, some of them specific to the Rosie. But we're going to talk about some of the pros and cons and why you may or may not want to do AC coupled. Some of the pros, it's less code headaches. It's easier to install, right? Like it's much easier to go ahead and put N-phase inverters on the roof and run 120/240 down, and you don't have your rapid shutdown requirements. You don't have all the DC cabling and conduit requirements. It's a more easy install, simpler to use type thing. So that is one benefit of AC coupled, is it can get you around some issues with permitting and inspectors and complexity of install. Another big one is it's much more efficient for daytime loads. So if you have a building, let's say you're in a doctor's office or some kind of manufacturing facility, and you're going to put a bunch of PV on there, having some AC coupled is nice because that doesn't get converted to DC and then back to AC. The loads come out of it first before it actually gets to the battery-based inverter. And then, one of the other pros really is it is just more familiar than DC. And that may seem weird to some people, and it may not seem weird to some people. A lot of installers out there have a lot of experience doing pure grid tie. They're doing N-phase, AP systems, or the likes of that, where it is all AC wiring. It's, the work is in that, and start to string together strings for DC charge controllers is something they're not very intimately familiar with, and it can make them a little uncomfortable. So rather than steering the customer away from a battery-based system, use it as an upsell and sell them an AC coupled system. That's another, kind of another one of those things where AC coupling can be a retrofit, right? Like, so if you've got a customer that has buyer's remorse, they call you up and they say, hey, I've got this $30,000 solar system, and every time the grid fails, my power goes out. How come? It's like, well, because you didn't want to buy the energy storage. So now we have to integrate the energy storage, and one of the easiest ways to do that is AC coupling by leaving everything else in place. So those are some of the pros. There's always can add to this list, right? We can talk about this one all day. Some of the cons, it's less precise on battery charging. So what I mean by that is if you've got an MPPT charge controller like ours or anybody's, it's infinitely adjustable, right? So if it's a 100 amp charge controller, it can regulate its output current in 1/10 of an amp steps all the way to 0. So as that battery starts to fill, it can slowly step down, 1/10 of an amp at a time, 1 amp at a time, whatever that may be, until the battery is full and it can properly charge that battery, which is super important on like a lead acid battery. Not so important on if it's a lithium as such, and also not so important if it's a battery backup system. So we'll talk a little bit more about that. If you have a system that is going to be off grid, and that's the whole goal of the system, then some DC coupling really is almost a requirement. You really want some of that controlled charging with that finite control. If the system is only there to back up the beer fridge during a power outage, then we're not quite so concerned about how we treat those batteries, because the batteries are probably going to die of old age before we wear them out, because normally your power outages are 2 or 3 times a year, right? And they don't last very long, maybe 5 times a year. So the battery is going to age out before you physically wear it out like you would in an off-grid situation. So there's a couple different ways you can look at that, and we'll talk a little bit about that in the sizing. Another con is, depending on your inverter, you may need a blackout relay for a generator. Like on the Rosie, for example, you will need a blackout relay. If you're using a Magnum, you'll need a blackout relay. If you're using like our all-in-one, you can get away without the blackout relay as long as you use the generator input on the all-in-one and the AC coupling input for your AC coupled. They will lock each other out in software inside. Another one is the potential overcharge of your battery if it's not set up properly. And this we'll talk about a little bit in the test of the system, functional test. But this is one of the big ones that we see where the installer will put it together and not actually enable the AC coupling or the frequency shift, or not put the blackout relay in. And then the battery-based inverter has no control. So it cannot control the charging when it's running in reverse like it can when it's in forward. it has to use that power. So if the grid tie inverter is forcing 5 kilowatts down its throat, it has to put that 5 kilowatts somewhere. It can't regulate that. Like when it's charging from the grid, it can just change its voltage a little bit to drop the charge current, and all is good. But on the grid tie inverter, the only choice it has is to either a frequency shift to throttle it, or it's just uncontrolled charge. So that's why it's important to verify after you program the functionality test. The Rosie also will not prevent the grid tie inverter from selling to the grid during grid up conditions. So if you've got a customer who says, I want to install a system, I do not want a net meter, I want to do self-consumption, then AC coupling may not be the way to go, because when the Rosie connects to that grid and the relay closes, it cannot prevent the backflow of power to the grid. Virtually no battery-based inverter can do that. If any battery-based inverter closes its relay, it's really out of control what's going back out to the grid from that grid tie inverter. So that's just something to be aware of. If the customer does not want that net metering agreement, probably steer clear of AC coupled. The other big one, then this is a big one. Well, it's not real big, but it's kind of a big one. This is a call to you as the installer when the problem happens. And this is a deadlock between your grid tie inverter and your battery-based inverter. And what I mean by deadlock is you've designed this system to power the customer's TV and beer fridge for 24 hours. Everything's good. Everything works perfectly. And the customer's like, I'm going to air fry my dinner, and I'm going to microwave this, and why don't I turn on the water heater? And they run their battery down, and the inverter goes into low battery cutout. When I say inverter, I'm talking about the Rosie or your battery-based inverter. It hits that low battery cutout, and it ceases making 120, 240 because it's trying to protect the battery. Now, at this point, the grid tie inverter goes offline. So now you have, what come first, the chicken or the egg issue here. And the only way to get that back online is to start the Rosie back up. So what I like to do on a AC coupled battery backup system is I like to set my low battery cutout a little higher than I normally would. So then when the customer calls and says, hey, I'm experiencing this problem, you're like, okay, you can turn the Rosie off, turn it back on, and it will boot up and it'll make power, and the grid tie inverter will come back on. Now keep an eye on your usage and don't overload it. That's just something to be aware of. Most battery-based inverters will have that issue. If you can get into something like a little bit of DC coupled with the charge controller, or like an all-in-one that has an MPPT input, they will, of course, charge the battery from the solar directly because it's DC coupled. But if it's purely AC coupled, that is a deadlock that you can get into. So it is sort of important to set that low battery cutout to a little bit of a higher standard. So I have a couple questions. One is, how are we handling inverter bypass? So let me back up if I can without causing too much problems. And here in this picture, this is what we call the MNE, Mary Nancy Edward 300 Rosie -240P, which stands for 240 volts primary. And you'll notice our part numbers are becoming much more explanatory now that Tony Boatwright's involved in them. We're doing a better job of that, I think. Right here in the middle, if you can see my mouse, are two white breakers. These may be black depending on the age of your E-panel, and they may be over here. The new rendition, they've moved over here to make the wiring easier for you straight up into the Rosie. And we switched to all the larger framed breakers, so the holes are all the same size. But you can just barely make out in this picture what looks like a piece of wire there. And we have what we call a Z-wire that interlocks the two breakers and gives you a mechanical bypass in the E-panel. So if the Rosie was to ever fail for any reason, you can flip that bypass, shut the AC input breaker off, turn your battery breaker off, and the Rosie is completely out of the question, and everything is just back to running off the grid. So all of our Rosie E-panels accommodate a bypass. The P100 has a 120 amp bypass for dual Rosies. If you were going to stack, say, like 4 Rosies, then we would need to do external switchgear. I have another question: what are the options for remote monitoring like Optics RE? And I mentioned earlier that we did partner with Solar Assistant to manage that monitoring and control for us. We are currently in beta with the monitoring, and they are working through a couple of quirks with some cables they have. They found they have a batch of bad cables in-house, and then they're going to get going on full programmability as soon as that gets resolved here, hopefully in the next few days. So we anticipate probably in the next 3 to 4 weeks being able to fully program a Rosie system as well remotely, not just monitor. So anybody that isn't familiar with Solar Assistant, I can maybe put I can send some information out. I was going to say maybe we could put a slide up at the end, but mine is actually offline because I'm testing some cables at the moment. But we can certainly get you all the information you want on Solar Assistant if you're not familiar with that. So another question I get a lot is, how do I size the Rosie? How do I size my battery-based inverter for my AC coupled, retrofit, if you will? Customer calls you and says, hey, I want to add battery storage. I want power when the grid goes down. Where do I start? And really, you have to look at it just like you would any other off-grid home, right? Like, what do they want to run? What's their largest load they plan to start, right? Like, do they have a 5-horse well pump that's, 1,000 feet in the ground, or do they have a half-horse well pump? And once you know, what's their worst load they're trying to start, and if that falls into a single Rosie, now single Rosie will start their hardest load, and then you kind of look at what they want to run combined together, right? Like, okay, they got a fridge, they got a freezer, they've got a couple TVs, some lighting. Maybe the max they've got is a couple thousand watts, easily goes into a single Rosie. Or maybe they've got some bigger needs and a bigger budget, and they actually want to expand that out and run a few more things. So a lot of times I find that budget will dictate the size more than customer wants. It's always this, go back to that scale we had in that earlier slide, where the customer puts all their wants in one side of the scale and they start filling the other with their dollar bills, and which one wins out. And usually the budget will end up kind of dictating what we back up, right? Because like off grid, you need to run it no matter what. You're off grid. But if you're talking about just during power outages, then we can be a little bit more selective, and maybe we can show the customer, hey, if you do 2 Rosies, yes, you can run that hot tub, but you're going to need 10 times more battery, and the system's going to cost X. But if we forget about the hot tub and we go to a single Rosie, we can do this for 10% of that cost that we quoted with the hot tubs, and you'll still power your beer fridge and your TV and your lights. So you kind of got to weigh that a little bit and size that there. And once you know the size of the system based on that information, like what do they need, what do they want, and then we have to look at the grid tie system, because the grid tie system does play a part in this sizing. So let's say that same customer has a 15 kilowatt grid tie inverter, or 14. Let's say 14 kilowatt. That's an easier number. Then it's a single inverter. The only choice we have is 2 Rosies, because we have to follow that 1-to-1 ratio, which we'll talk about a little bit more. But if the customer has, say, multiple strings of microinverters like N-phase or AP systems, then we can look at it and decide, hey, do we want to split those up, or do we want to put in 2 Rosies? Because let's say that same customer has 14 kilowatts of microinverters. Now what we can do is we can go up there and we can peel 1 or 2 strings out of the panel, the electrical panel, and feed them into the Rosie's backed up panel as AC coupled. And we have still met the 1-to-1 ratio. We've met all the customers' needs, and yet we've also kept their budget down on their backup, right? Some of the solar goes directly to the grid, some goes to the AC coupled. So those are the sort of the bullet points of sizing, right? Like, what is the grid tie system comprised of? Can it be broken down into pieces that will fit on a single Rosie? What is the customer's needs? What is the customer's budgets? And what is the customer's wants, right? Because if the customer wants to power their hot tub and their budget allows that, all the power to them and all the power to you for installing that system, because that will be a nice system. And, but a lot of times I find that it's not always well known what it takes to power certain loads. I had a caller the other day that said, I want a really small system. It's really simple. I want to run my central air conditioner and my refrigerator 24/7. I'm like, that's not a small system, depending on your central air conditioner. So, there's a lot of education in that. And it's one of those things where if you do that education properly as an installer with that customer will be happy with the system. They will refer you to other customers, and everybody's happy. If you try to kind of undersize the system to keep the budget down, and the customer has a bad experience, and then it goes the other way, and they're running around telling how you didn't design the system right or whatever. So that it really pays to get that right, and it's also very important that you become a very good detective with that customer, because a lot of times customers will forget about things that they want to be powered. They don't really think of it like you or I do, because we know every kilowatt is a kilowatt we got to produce and store. The customer may not really think like that. So I like to sometimes just really walk around with the customer and be like, oh, what about that? Do you want that on, or what about this? And another thing you can do that I've had great success with is to give the customer some form of an energy monitor for a month in advance, for example, and let them experiment with their own loads and see how much each thing is responsible for when it comes to their, current light bill. So those are all kind of just like little tips and tricks, if you will, that help you size how you're going to size the battery-based portion of this system. And then we get into the battery. The battery is one of the points where we can go several ways. Again, we have to determine a lot of things here, like what does the customer want? Is the customer like, I only really need like 8 or 10 hours of backup and that's all I want to pay for because my grid usually only fails for 3 or 4 hours and I'm covered? Or is your customer up in New England somewhere where they can get an ice storm and they can be without power for 5 days and they want 3 or 4 days of autonomy, just like a basic off-grid system? So again, that's where you can kind of look at it and you can say, okay, well, here's how much you need for a 24-hour block. Here's what it would be for 48, and here's what it would be, for 3 days. And in that same mentality, if you're sizing that battery and building that battery for a battery backup system for just utility outages, we can be a lot more aggressive with that battery. Like, the old analogy of if I've got a lead acid battery, never drain it below 50% ever, ever, ever. Well, if you're using an AGM type battery and it's a battery backup system for the utility grid, you can be a lot meaner to that battery because the outages are fewer and far between. And again, it comes back to that. The battery is going to age out before it wears out. So we may go ahead and beat that AGM down to 25% state of charge instead of 50 to save that customer some initial investment because they're not going to wear that battery out. They're going to age that battery out. But if the customer is doing a system that is sort of like semi off grid, then you have to follow all the the normal rules because now you are going to wear that battery out versus aging it out. So again, do your load calculations for a 24-hour period, figure out how much they want to back up. If they only want 12 hours, you divide it by 2 and add a little for your cushion. If you're using lithium, you can be down to the 20% state of charge easy. If you're using lead, maybe stay around 25 if it's a backup. And again, if it's off grid, we typically say 3 days of backup and try not to go below 50% on a lead acid battery. You can dig deeper, of course, into a lithium. There are tons and tons of charts. We have published documentation, I believe, on our power flow that will tell you the difference between draining it to, say, 25% state of charge regularly or 50% state of charge, like 75%. There is a difference in cycle life, but you have to calculate, is that difference better to oversize the battery and dig shallower, or is the cost of the additional battery, outweighed by, digging deeper into that battery? So you have to balance that out based on cycle life. And then, the current limit of the battery versus the grid tie inverter is another thing to look at. So what I mean by that is, like, let's say in step 1, the customer determines they only want 6 hours of backup, and your math says they only need 4 kilowatt hours of battery. So you're like, perfect, I'll throw a PowerFlow 5 in there. I've got 5 kilowatts of battery backup. I've got a Rosie. I've met the customer's needs 100%. But then you didn't catch the fact that you had 7 kilowatts of grid tie inverter. And when the grid fails, the Rosie is going to charge that PowerFlow 5 at 120 amps, and you've exceeded the charge limit of the BMS, and the BMS is going to open and the system's going to shut down. So those are your 3, sizings, if you will. Look at how much current the grid tie inverter is going to force into that battery, and make sure your BMS or your lead acid battery is capable of accepting that current. Look at the customer's needs, and then go from there. Also look at the inverter's recommendations. Some inverters have a pretty stiff recommendation for amp hours or kilowatt hours of battery per kilowatt of inverter. The Rosie is a lot less picky than some. You can run a Rosie on, a 5 kilowatt hour server rack battery. I would personally suggest 2 as a minimum. The all-in-one, I think, is about in that same ballpark, but some other competitors' inverters do have some requirements on minimum battery capacity. So do be aware of that one as well if you're not using a Midnite inverter. But you should be using a Midnite inverter. So what does happen if something causes the grid tie inverter to exceed the Rosie's rating? So you'll hear, this is where we're going to talk about one-to-one ratios and, GT to battery-based inverter, grid tie to battery-based inverter, sizing ratios. Some inverters, if you exceed the limit, the inverter will break. Some inverters can regulate. SMA Sunny Island was really good at regulating and not being damaged. The problem with regulation, though, is the only way it can regulate, remember, is by frequency shifting and knocking the grid tie inverter offline. So yeah, you could put a 10 kilowatt grid tie inverter on a 7 kilowatt Rosie. You will not damage the Rosie, but every time the power fails, the Rosie is going to have to frequency shift to protect itself and knock the grid tie inverter offline. But what that does allow you to do is run a true one-to-one ratio on the Rosie. So if you have a 7 kilowatt grid tie inverter and you get an edge of cloud and it bumps up to 8,500 watts or 9,000 watts, the Rosie doesn't care. The Rosie reacts the same way in reverse as it does in forward. It will watch temperature rise internally and it will regulate based on that. So eventually the temperature will rise because you're overdriving it, and it will AC, it will frequency shift and knock the AC coupled offline. So with that being said, our recommendation is a one-to-one ratio. We recommend no more than 7 kilowatts of grid tie per Rosie. And don't count your loads. This is another one that I hear a lot. It's like, well, the customer always has a static load of 2,000 watts. Well, that may be true most of the time. Eventually, Murphy's Law is going to kick in, and the customer is going to shut off some of those loads. And what you may have counted on to burn off some of that grid tie inverter is no longer present. And what I mean by that is, like, if you picture that grow watt on the left is 10 kilowatts, and it's back feeding the Rosie on the right, the loads come from between those two. So if the customer had 3 kilowatts of AC load on, the Rosie would only see 7 kilowatts. So it would never regulate and everything would be perfectly happy. But if the customer shuts off that 3 kilowatt load, all of a sudden the Rosie is going to see 10 kilowatt and the system's going to shut down and the customer is going to call you. So we suggest one-to-one ratio. Make sure the grid tie inverter is no more than 7 kilowatts per Rosie, and or split up the grid tie system if it's made of inverters that allow you to do that, like microinverters or multiple string inverters. Just for optimal system performance and lack of callbacks, that's going to give you that, just bulletproof system. And I don't think I have a slide that talks about the actual frequency shift as such, but I will talk about it when we get to programming, so bear with me on that one. So in a AC coupled scenario, we would simply land the grid tie inverter into the critical loads panel. So if you're familiar with installing a battery-based system, let's just say over here on the right side of the Rosie, and I apologize, I should have a really nice graphic here, and I just haven't got one built yet. But let's say we got the telephone pole over here on the right side of the Rosie and our main breaker panel over here. We got 200 amp service feeding our hot tub and our refrigerator and all, not a refrigerator, our electric stove and all that. We feed into the Rosie with a 60 amp 240 volt feed for a single Rosie. We come out of the Rosie to a critical loads panel, or backed up loads panel, if you will, over here. And that backup loads panel is what will be on during an outage. The grid tie inverter will feed into that same backed up loads panel, and that way it's connected to the AC out of the Rosie. There are not provisions inside the Rosie ePanel to make that connection. You could do it using some Polaris connectors, and you could stick another breaker in here. There's space for another breaker. You could land it there, but we recommend landing it right in the backed up loads panel or the critical loads panel. We talked about how to split it if you've got like microinverters and some of it has to go around. And in that case, you'd have a couple strings of micros going to the critical load, a couple strings bypassing and staying right over in the main panel where they always were. That's what we mean when we say splitting the grid tie inverter. And you can also add DC coupled to this, and there is no limits other than the battery charge rate with DC coupled. So what would happen is, let's say you have that 7 kilowatt grow watt. We go back here. You have this as 7 kilowatts, you have the Rosie as 7 kilowatts, and let's say you put a Barcelona over here with 10 kilowatts of PV on it. What would happen during a grid outage is the battery voltage would rise, the Rosie would knock the grow watt offline. It would throttle it back and then knock it offline, and the Barcelona would just finish the finite charging of the batteries. And if the battery voltage drops because the Barcelona can't keep up, then the grow watt would come back online after its 5-minute timer counted through. So we talked about the generator blackout relay a little bit, but this is something that I kind of wanted to go a little deeper into. So let's say your customer is that customer in New England who says, hey, I could be without power for 7 days where I'm at. And I can speak to that because my local utility where I live in Maine is optional. We pretty regularly lose our grid for 6 to 10 days during the winter, multiple times a winter. So if that customer is in that boat and they're like, hey, I want to integrate my backup generator as well, then you're going to put in a transfer switch to select generator or grid to the Rosie. And this is where, if it's AC coupled, we need to get into what we call a blackout relay. Because remember, the Rosie, just like any other battery-based inverter, if you connect an input to its input, it's going to close its relay. And once it closes its relay, it connects the grid tie inverter to that input, which in this case is now a generator. And most generators do not appreciate being backfed from the grid tie inverter, especially if it's a small wheels and handles style generator. So what we normally do is we use a 2-pole, normally closed relay of a 240-volt coil. What I do is I just tap right in my transfer switch, and I take the 240 volts from the generator, feed to the coil of the relay, and then the contacts in the relay I use to break the generator feed to the grid tie feed to the sub panel. So it's a little complicated to explain without a drawing, but I can certainly send you wiring diagrams if you need it. If you explain your situation, I can customize the drawing to your situation. But essentially what we're doing is we're putting a 2-pole relay between the grid tie inverter and the critical loads panel, and we're driving the coil of that relay from the generator's 240 volts. So whenever the generator makes 240 volts, the grid tie inverter shuts off, and that keeps the two isolated from each other. So I do have a question. What is the max distance for the separate monitor screen for the Rosie? And is it just a normal 6E Ethernet cable? So yes, the Rosie uses a MNGP2, as shown there in the top left corner. Those come on the charge controllers or come with a pre-wired Rosie, or optional, not optional, but you have to buy it optionally if you're buying the parts to put together. And I would say that you're probably good to 400 or 500 feet. It comes down to the voltage drop on the 9-volt line to power the display in the display. I have tested personally to about 350 feet using standard Cat5 cable. It is a standard Cat5 pinout, so you could use Cat5, Cat6. So the smaller the number, the larger the wire, the farther you can go, because it's a voltage drop issue. So that, we've tested to about 350 feet. We can certainly test to more if that need arises. If you're going that far, you might really want to look into something like the Solar Assistant and doing it through Wi-Fi, because you start getting that long, you're starting to build some really big antennas directly into the CAN bus. The CAN bus is isolated, but during lightning strikes and stuff, that is something that's often overlooked, and damage can be occurred through the communications lines. So programming, we're going to assume the basic programming is done, and anybody that does need assistance with that, we have a lot of videos, we have some documentation. I have full menu maps for all of this that I can provide. Happy to work with you on that. But when you first fire up the system, it's going to ask you to give it a name, set all your settings, what type of battery is it, what are my programming charge points, and, time and date. And time and date's important. We just worked a tech support call, actually, that the customer's system was waking up in float every morning. And it took us a few minutes to find it, but they had the time set for AM instead of PM. So the units were thinking that midnight was actually happening at noon, and it was starting a new bulk charge at noon instead of midnight. So that's one that's important to get. But it asks you all that on startup. It walks you right through it, and then it goes to work. If you're doing closed loop, that stuff is not critical, because the closed loop commands everything to happen, by default. But I recommend setting it anyways, because if somebody was to unplug a cable, a mouse chews through the wire, whatever the battery's BMS quits talking. I've seen that on a couple different brands of batteries. The system will default back to open loop and not just shut down. So it will give you a fault that it's, that there's BMS issues, but it won't leave you in the dark. It will keep running in an open loop environment. So setting those 3 or 4 settings is important. But assuming all that's done, really all we have to do to actually make AC coupled work is, as I mentioned, we want to set up our low battery cutout properly to leave a little room, maybe make it trip off at like 25% instead of 0%. And then set your reconnect a couple volts above low battery cutout. This one's important. I worked one the other day where the customer thought the Rosie was defective because it was shutting off 2 or 3 times in the night, but it would come right back on in about 10 seconds. And what we found was the low battery cutout was set for 48, and the reconnect was set for 48.5. So as lithium batteries, when a load would come on, would dip to 48 for the, there's a time you can set as well, a delay time. And it would go past that time, so the Rosie would stop making AC, and then just once the load is gone off the battery, it would bounce back to 48.5, and the Rosie would start right back up. So I recommend a couple volts because you really need to get some charge back in there before you start using that battery again. Set your disconnect time for about 10 minutes. This is that delay we were talking about. So what that means is that if the well pump comes on and the battery momentarily dips below that 48 volts, it's not instantly going to shut off. You can set this for any number you want, but I find 10 minutes is a good compromise of, getting through that well pump running versus the battery just being low. And then in setup, inverter config, Rosie, AC input. So the bold here is actually the menu process you'd follow. You'd press the setup button, you'd scroll to battery config and enter that. Press the setup, scroll to inverter config, enter that, scroll to Rosie, enter that, AC input. Here we would set the mode to grid, which it is by default, but we want to verify that. We want to set the breaker size accordingly if it's less than 30 amps, because this will limit what the GT inverter can do if you set it too low. In the system setup, so setup button, system config, and then we scroll down and we turn AC coupled to on. And what that's going to do is that's going to frequency shift. So what the Rosie does is it follows a fairly prominent UL 1741 SASB type curtailment, if you will. So what it does is it frequency shifts up into the 62 hertz range to curtail the grid tie inverter. So if you have a grid tie inverter that is capable of 1741 SA or SB, the Rosie can throttle it back. I believe it's 4 steps. So the first thing it'll do is it'll kick it back 25%. And then if that doesn't fix the problem within 90 seconds or so, it'll kick it back another 25%. And it can do that all the way up until it kicks it to 0. And then if you're throttling like that, when it starts to back off, and if a load comes on, the frequency will drip back down and the grid tie inverter will ramp back up. So it's a pretty elegant solution. If you've got an older inverter that doesn't support SA or SB, the Rosie just simply shifts the frequency anyways, which the first step is outside of that inverter's window, and it just goes offline. And then when the voltage drops back down, that inverter will count its 5 minutes and then reconnect and start charging the battery. So that's really it. These are all things that should be set anyways. The low battery cutout, that should be programmed by default. Your input and all that should be programmed by you when you install the system as well by default. This isn't AC coupling specific. And honestly, on the AC coupled, there's really no downside to it being on either, even if you don't have an AC coupled inverter, because it's only going to frequency shift when the battery is at or above its target. So I'm going to try to wrap up with the theory of operation and the how to test this. So we've sort of talked about the theory of operation, but essentially under normal conditions, the Rosie closes its relay and it just looks like it's not even there. The grid tie inverter sells to the grid, everybody's happy, everything's doing what it's supposed to do. But when the grid is down, when the telephone pole looks like that and the power is off, then the grid tie inverter, the Rosie stays on, it opens its relay, the grid tie inverter then is fooled into thinking the grid is there, and it helps, maintain the loads, charge the battery. If the GT inverter is not making enough to cover the loads, the Rosie will add what's needed. So let's say it's a day like this and it's snowing and the grid tie inverter is making 500 watts and the load is 3,000. The Rosie will power 2,500 from the battery. But now let's say the sun comes out and the grid tie inverter is making 7,000 watts and the load is 3,000. The Rosie will take 4,000 watts and put it into the battery after the loads are satisfied with the first 3,000. So it kind of, it uses everything it has to is the loads are priority, I guess is the way to say that. Loads first, battery second when you're AC coupled. When the battery is close to full, when it gets close to its target, or if it's closed loop, when the BMS starts saying throttle back because I'm full, then the Rosie will frequency shift. And like I talked about, it does it in 4 steps, and it follows that SA/SB. And I don't know the frequencies offhand. I can get them for you if you need them. But I believe the first step is just over 52 hertz, 62 hertz. I don't know why I'm stuck in European mode today. 62 hertz, and then it bumps up a little bit more until it gets to the one that forces it offline. The Rosie should also be set to charge the battery for short float time. This is another one. You don't want the Rosie floating 24/7. This is sort of true of any grid-connected Rosie system. In the battery config menu, you'll find a float time which defaults to 24 hours. You want to set that down to something more reasonable, like 1 or 2 hours if you're grid-connected. Now, that doesn't affect the charge controllers. If you're DC coupled, the charge controllers will float all day long as there's sun out. But what that does, it allows the Rosie's charger to go silent and quit buying power from the grid. So that's another little thing to check. So this is I think my final slide, and this is my functional test. So there's a couple of caveats to this. The battery needs to be close to full, and you really need a sunny day, pretty sunny day. So what you're going to do is you're going to roll to the site on a pretty sunny day. You're going to get the battery up to 90% state of charge or whatever, get it close to full, and you're going to make sure the loads are less than what the grid tie inverter can produce. Ideally, you would have the loads just powered from the grid. Put that whatever, get them off the Rosie for now. But you got the system running. You fail the grid with the voltmeter connected, and what you should see is as the state of charge gets up in the 98 to 100% range, you should see the frequency start to rise up to 62 hertz. And what you should see, if you're watching like the MNGP2 for your battery voltage and you're watching your Fluke for frequency, you should see the battery voltage stabilize on the MNGP2, and the frequency will stay at that step. And what you'll see is it won't stabilize, right, because you've turned the loads off, and that battery voltage is going to keep climbing up, and you'll notice the frequency will jump up those 3 more steps. And when they do, the grid tie inverter will drop offline. So once that's done, then what you do is you start putting loads on the inverter and bring that battery voltage back down and verify that the frequency drops back down to 60 hertz so the grid tie inverter can kick online. So it's a pretty simple test, but you do want to run through that function test. And if you have a blackout relay on a generator, also a great time to test that. Make sure that when that generator starts, the grid tie inverter goes offline instantly. That's a pretty simple test, but just verify that. And that's kind of it. I know I went long on you guys, and I appreciate you all sitting here and listening to me blabber for almost an hour. We had a few questions. I'm open to questions. Go ahead and put them in the question pane if you like. I will answer them. And as I said, here's our contact information. Mine is ryan@midnitesolar.com. So if you have specific design questions, criteria, or you'd like a wiring diagram for something, just give me a shout. We'll help you out. We've got tons of canned drawings already, and we can customize a drawing to your needs pretty quickly.
Thank you all for joining us. If any of you do need that NABCEP certificate for the continuing education credit, again, just email sales@midnitesolar.com and we'll get that out for you.
All right, well, we don't seem to have any questions, Sue, so I think we'll go ahead and wrap this up. And we really appreciate everybody taking that hour out of your day and listening to me. I do have one question. Always off-grid situation. Can we assist loads between a Rosie and a generator? Say Rosie is feeding, but not enough. Can Jenny kick in and help? Yes, that can go both ways. So Rosie has what we call load transfer. So you could tell it, hey, if the load exceeds a certain amount, pull in something on the input, be it generator or grid, and run the load. But it also has what we call grid support, which is like a generator support type thing, where if you have let's say you have a 5 kilowatt generator running and you've got a 7 kilowatt Rosie available, and you turn on a 10 kilowatt load, the Rosie will pull the 5 kilowatts or whatever you have programmed to pull from the generator. It'll pull the remaining from the battery to support that load. When the load goes away, it'll go back to charging the batteries. So it can assist in either direction. So yes, you can command it to bring an input on when the load exceeds something, or you can also ask it to assist the input if the input is, not capable of plowing the loads. All right. Appreciate it, guys, gals. Thanks for coming out. Thanks for spending an hour with me. Look forward to doing another one, maybe even next week, on curtailment modes in the Rosie. That's going to be an exciting one. And yes, mobile Rosies also can AC couple. The only difference between the mobile Rosie and the regular Rosie is a neutral to ground bond switching relay. There are a few subtle changes in the code. A mobile Rosie will auto detect what's on its input. So if you plug it into 122.08, it'll auto detect that and connect and use it. It'll auto detect 120 on both legs. So if you're in an RV park and you connect with a 30 amp dog bone, the Rosie will just take the 120 on both legs and operate to that on the mobile Rosies only. So the mobile Rosie will auto detect its input. The renewable energy Rosie, you pick the input because we want it to stay the same. So, all right. Thank you, everybody, and have a great day. Hopefully it's sunny and warm where you're at.